The universe appears as a whirlwind of chaos and chance, but underneath the noise, a silent, perfect order is written in the language of mathematics. From the grand spiral of a galaxy to the delicate arrangement of a flower's petals, numbers and equations shape everything we see. This journey through 25 astonishing phenomena will reveal how a hidden mathematical structure governs reality itself. You will discover the secret patterns that connect the smallest particles to the vast cosmic web. We will see how a simple sequence dictates the growth of life and how the orbits of planets follow an elegant celestial rhythm. What single idea about our world will this mathematical order change for you forever? Those spirals in the sunflower are not a random accident. They are a perfect signature, a code written into the very blueprint of life. This code is the Fibonacci sequence, a simple list of numbers that begins with 0 and 1. Each new number is just the sum of the two before it, so it goes 0, 1, 1, 2, 3, 5, 8, 13, and on into infinity. A man named Leonardo Fibonacci presented this idea in the early 1300s, but he was merely describing a pattern the universe had already perfected. You can find this same sequence in the unfurling leaves of an artichoke, the curve of a nautilus shell, and even the swirling form of a hurricane. Why would such different things share the same mathematical rule? The answer lies in a concept of ultimate efficiency known as the golden ratio. As the Fibonacci sequence grows, the relationship between consecutive numbers gets closer and closer to this special ratio, approximately 1.618. This ratio represents a proportion that is remarkably efficient for packing and growth. Think of a tree. Its branches spiral around the trunk following Fibonacci numbers. This specific arrangement ensures that every leaf, positioned at a certain point along the spiral, avoids being directly shaded by the leaves above it. It is nature's brilliant solution for catching the most sunlight. The universe seems to have a preferred method for building things, and that method is written in the elegant, recurring language of Fibonacci. That same ratio of 1.618, the golden ratio, is far more than a rule for flowers. It is a fundamental blueprint, a cosmic constant that seems to stitch the universe together from the smallest scales to the largest. Take the spiral of a nautilus shell. Its beautiful curve is not arbitrary. As the mollusk grows, it constructs each new chamber of its shell in proportion to the last, adhering precisely to this golden ratio. This creates a logarithmic spiral, a shape that expands without ever changing its fundamental form. It is a perfect snapshot of balanced growth, and this very same spiral shape is written across the cosmos. The grand spiral arms of our own Milky Way galaxy and countless others follow this same mathematical curve. How can a sea creature and an entire galaxy, two things separated by an unimaginable gulf of space and complexity, share the same architectural plan? The connection runs even closer to home. Look at your own hand. The ratio of the length of your forearm to your hand often approximates the golden ratio. The segments of your fingers, the proportions of your face, the arrangement of your DNA's double helix, all whisper this same number. This is why artists and architects from the ancient Greeks to Leonardo da Vinci were so captivated by it. They saw it as a divine proportion, a secret to beauty and harmony. Euclid defined it mathematically, and Da Vinci meticulously illustrated it in his Vitruvian Man, overlaying the ideal human form with the perfect geometry of a square and a circle. Mathematically, the golden ratio is an irrational number, meaning its decimal digits go on forever without repeating. it is a number that resists being pinned down to a simple fraction, embodying an infinite and elegant complexity. Its prevalence is a profound clue. It suggests that the universe has a deep-seated preference for certain forms, a hidden standard of efficiency and beauty that governs everything from the way we are built to the way galaxies spin. This ratio is a silent thread connecting the microscopic world of biology to the macroscopic realm of the stars. Johannes Kepler stared at the heavens and saw a hidden geometry. In the early 1600s, while others still clung to the ancient idea of perfect circular orbits, Kepler uncovered a different truth. The planets, including our own Earth, travel around the Sun not in circles, but in elegant, oval-shaped paths called ellipses. This was his first revolutionary law. His second law revealed another secret, that a planet speeds up as it gets closer to the Sun and slows down as it moves away, sweeping out equal areas in equal times. It is a cosmic rhythm, a gravitational dance with precise timing, but it was his third law that truly connected the solar system with a mathematical thread. He found that the square of a planet's orbital period, the time it takes to complete one orbit, is proportional to the cube of its average distance from the Sun. This single equation ties the entire solar system together. A world that is 8 times farther from the Sun than another will not take just 8 times longer to orbit. The relationship is far more precise and mathematically beautiful. Kepler himself used the puzzling orbit of Mars with data carefully recorded by his predecessor Tycho Brahe to unlock this celestial code. He showed that the heavens were not guided by mystical forces, but by a predictable mathematical order. This insight transformed our understanding of the cosmos and provided the essential foundation for Isaac Newton's later theory of gravity. What do these elliptical paths reveal? They are the signature of a force, a silent, invisible hand shaping the motion of worlds. Kepler's laws are not just historical footnotes. They are the active rules that engineers use to calculate the trajectories of every satellite and space probe, guiding our exploration of the cosmos. His work proved that the universe is not only mathematical, but that its deepest laws are accessible to the human mind. Light itself holds a secret identity. It can be a continuous wave spreading out and interacting with itself, or it can be a stream of tiny, discrete packets. This wave-particle duality is one of the most intriguing and fundamental puzzles of the quantum world. For centuries, scientists debated the nature of light. Isaac Newton argued it was made of particles, while others like Christian Huygens demonstrated its wave-like properties, such as interference and diffraction. The truth, as we now know, is that light is both, and which face it shows depends entirely on how we choose to observe it. The most famous demonstration of this unique behavior is the double-slit experiment. Shine a beam of light through 2 narrow, parallel openings onto a screen. If light were simply particles, you would expect to see 2 bright lines, but that is not what happens. Instead, you see a series of light and dark bands, an interference pattern. This is the clear signature of a wave, where peaks and troughs overlap to create areas of brightness and cancellation. Now, here is where the mystery deepens to its core. If you send individual particles of light, called photons, through the slits one at a time, they still build up that same interference pattern over time. It is as if each single photon passes through both openings at once and interacts with itself. This result challenges the very foundation of classical logic. How can one thing be in 2 places at once? Albert Einstein was instrumental in revealing the particle nature of light, proposing that energy is quantized into discrete packets, or quanta, an idea for which he later won the Nobel Prize. His work on the photoelectric effect showed that light could release electrons from a metal surface, behaving not like a gentle wave, but like a stream of tiny projectiles. The mathematical description of this duality is equally elegant. The energy of each photon is proportional to its frequency, a simple equation that ties the particle nature of light directly to its wave nature. This is not just a theoretical curiosity. Our entire modern world depends on this quantum paradox. Lasers, which rely on the stimulated emission of identical photons, are used in everything from surgery and barcode scanners to the fiber optic cables that carry the internet. Electron microscopes use the wave nature of particles to see details far smaller than any light microscope could ever reveal. This duality invites us to accept that at the most fundamental level, the universe is not deterministic in the way we experience it. Reality is probabilistic, governed by mathematical wave functions that describe the likelihood of finding a particle at any given point. The line between a spread-out wave and a localized particle is not a hard boundary, but a fluid mathematical expression. This hints at a deeper, unified structure where what we call a wave and what we call a particle are merely two different views of the same, hidden mathematical object. That same fluid logic of the quantum world finds a strange echo in the very shape of our reality. Look closely at a rocky coastline from high above. Its ragged edge is not a smooth, simple curve. Zoom in on one small bay, and you find a pattern of inlets and headlands that looks remarkably similar to the entire coast. Zoom in again on a single headland, and its own miniature coves and rocky points repeat the pattern once more. This is not a perfect copy, but a persistent, self-similar complexity that goes on, down to the cracks in a single stone. This is the fingerprint of a fractal, a shape whose intricate detail repeats at different scales. The mathematician Benoit Mandelbrot gave these shapes their name in the 1970s, recognizing that this rough, fragmented geometry was the true geometry of nature. Fractals are shapes that are self-similar and infinitely complex. A cloud is not a sphere, a mountain is not a cone. They are fractals, built from patterns that recur as you look closer and closer. Their formation comes from an elegantly simple process, iteration. A basic mathematical rule is applied, then its output is fed back in as the new input, over and over again. This recursive process can generate astonishing complexity from a seed of simplicity. The most famous fractal is the Mandelbrot set, a single equation that, when iterated, produces an image of infinite depth and beauty. No matter how far you zoom into its boundary, you will never find a smooth edge, only an endless, swirling parade of self-similar shapes. This is not just a mathematical curiosity. Our lungs are fractals. The branching network of airways maximizes surface area within a limited volume, allowing us to absorb oxygen with incredible efficiency. The network of blood vessels in your body does the same, reaching almost every cell with a fractal pattern. And on the grandest scale, the cosmos itself appears to be arranged in a fractal-like structure. Galaxies are not scattered randomly through space. They cluster into groups. Those groups form larger clusters, and those in turn create vast filaments and walls that stretch across the universe. A cosmic web of unimaginable scale that mirrors the branching patterns of a tree. Why would such a geometry be so universal? Fractals reveal a profound truth about how complexity is built. The universe seems to favor a method of construction where simple, repetitive rules, applied again and again, generate the rich, textured world we see around us. It suggests that the apparent chaos of a forest, a mountain range, or a galaxy is merely the surface expression of a deep, recursive order. The same mathematical harmony that guides a musical chord also conducts the grand dance of the planets. Throughout the solar system, moons and planets fall into step with one another, their orbital periods locking into perfect, simple ratios. This celestial synchronization is known as orbital resonance. Consider Jupiter and 3 of its largest moons. For every single orbit that Ganymede completes, Europa circles exactly twice, and the volcanic moon Io races around precisely 4 times. This 1:2:4 ratio is a gravitational symphony, a repeating pattern of gentle influences that keeps their paths stable and predictable. The discovery of these resonant chains is credited to the brilliant French mathematician Pierre-Simon Laplace, who saw the clockwork mathematics within the apparent complexity of the heavens. These resonances work because gravity, acting over vast distances, provides a steady, rhythmic push. Each time the orbiting bodies return to the same alignment, their gravitational influences reinforce one another, like a parent giving a child on a swing a small boost at just the right moment. This repeated encouragement prevents their orbits from drifting into disarray, effectively building a protective, mathematical corridor through space. Even tiny, distant Pluto is part of this dance. It is locked in a 2:3 resonance with the giant Neptune. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This ensures that when Pluto's elliptical path brings it closer to the Sun than Neptune, the 2 worlds are always on opposite sides of the solar system, forever maintaining a safe distance. What invisible force compels these celestial bodies to keep such perfect time? The answer lies in the universal language of mathematics, which orchestrates this cosmic ballet with the same elegant ratios found in a vibrating string. This is not a quiet order, but a dynamic, rhythmic one, a fundamental pulse that maintains the harmony of our solar system and far beyond. These cosmic rhythms are orchestrated by a set of unchangeable numbers, the fundamental constants of physics. The speed of light in a vacuum is always exactly 299,792,458 meters per second, a universal speed limit that nothing can exceed. Planck's constant defines the smallest possible action in the quantum realm, the tiny packet of energy a photon can carry. These are not just numbers we measured. They are the immutable rules written into the very foundation of reality. They appear in our most profound equations, from Einstein's elegant E=mc², where c is that constant speed of light, to the law of universal gravitation, which depends on the gravitational constant, big G. These values were not invented. They were uncovered through careful and persistent experiments, like the sensitive torsion balance used by Henry Cavendish to first weigh the Earth and measure G. Their precision is breathtaking. If the strength of the electromagnetic force were even slightly different, the bonds between atoms would weaken. Stars would either never ignite or would fade away in a cosmic instant. The fine structure constant, a pure number that governs the strength of electromagnetic interactions, is so exquisitely tuned that even a change in its 4th decimal place would prevent carbon, the essential element of life, from forming inside stars. Why does our universe possess this seemingly perfect set of numerical rules? It is as if the cosmos was constructed upon a bedrock of mathematical relationships that allow for complexity and ultimately for us to be here to observe it. This fine-tuning points toward a profound possibility that the laws of physics themselves are the ultimate expression of a hidden mathematical order, a consistent framework that makes existence possible. These prime numbers, the fundamental atoms of mathematics, guard our digital world. They are numbers greater than 1 that cannot be divided evenly by any other number except 1 and themselves. 2, 3, 5, 7, 11. The sequence continues infinitely, as the ancient Greek mathematician Euclid elegantly proved over 2,000 years ago. Yet for all their simplicity, their appearance along the number line is a profound mystery. They seem to scatter without an obvious pattern, a tantalizing mix of order and chaos. This very unpredictability is what makes them the perfect foundation for cryptography. Modern encryption, like the widely used RSA algorithm, relies on a simple but powerful concept. It is easy to multiply two large prime numbers together, but incredibly difficult to take the resulting massive product and figure out which two primes were used to create it. Your online banking, your private messages, your secure logins, all are protected by this mathematical one-way street. The security of our entire digital society hinges on the scattered distribution of these indivisible numbers. But is their distribution truly random? The Riemann hypothesis, perhaps the most famous unsolved problem in mathematics, proposes a deep, hidden order underlying the primes. It suggests that all their apparent randomness is governed by the behavior of a specific mathematical function, a zeta function, whose non-trivial zeros are thought to form a perfect line in the complex plane. Proving this would revolutionize our understanding of number theory and potentially the security of the encryption we depend on. This mathematical order even finds a mirror in the natural world. A species of cicada in North America spends 13 or 17 years developing underground before emerging as adults. Both 13 and 17 are prime numbers. Researchers believe this prime-numbered life cycle is an evolutionary strategy to avoid predators. If a predator has a 2, 3, or 4-year population cycle, it will rarely synchronize with a cicada emergence that only happens every 13 or 17 years. This is nature using prime number theory for survival. From the deepest abstractions of mathematics to the rustling of insects in a forest, the unique properties of primes reveal a hidden layer of structure. They are the immutable building blocks not just of numbers, but of security and life itself, a silent mathematical order operating behind the scenes of our existence. Deep within the heart of every atom, an unseen symmetry governs the dance of creation and transformation. This is not a symmetry of shape, but of action, a set of perfect, unbreakable rules that guide how the universe's fundamental building blocks interact. The mathematical language that describes this hidden architecture is called group theory. It provides the framework for the standard model of particle physics, a set of equations so powerful it can predict the existence of particles before they are ever observed. The most famous example of this predictive power is the Higgs boson. For decades, its existence was a necessary consequence of the mathematical symmetry of the model, a missing piece required to complete the puzzle. Its eventual discovery in 2012 was a monumental triumph, not just for physics, but for the idea that reality is fundamentally mathematical. The connection between symmetry and physical law was profoundly illuminated by the mathematician Emmy Noether. She proved a breathtakingly elegant theorem that for every continuous symmetry in nature, there is a corresponding conservation law. The fact that the laws of physics are the same today as they were yesterday, a symmetry in time, directly implies the conservation of energy, the rotational symmetry of space, the idea that the outcome of an experiment does not depend on which direction you face, leads to the conservation of angular momentum. Her work showed that these deepest principles of physics are not separate rules, but direct consequences of the universe's inherent mathematical harmony. This unity is beautifully displayed in the organization of subatomic particles themselves. In the 1960s, physicists Murray Gell-Mann and Yuval Ne'eman independently used a specific symmetry group to bring order to a zoo of newly discovered particles. They called this the eightfold way. Just as a crystal can be rotated to reveal its symmetrical facets, These particles could be arranged into geometric patterns based on their properties, patterns that pointed directly to the existence of even more fundamental constituents, the quarks. Why does our universe seem to be written in this language of symmetry and group theory? It is as if the cosmos is built upon an invisible lattice of perfect, abstract relationships. The energetic spray of particles produced in a high-energy collision is not random chaos. It is the elaborate yet predictable outcome of a deeper, more beautiful order. The next phenomenon reveals a pattern so simple a child can understand it, yet it holds the key to predicting everything from the weather to the flow of the stock market. That elegant order of the cosmos conceals a deep-seated sensitivity, a fragility that reveals itself in the very air we breathe. A butterfly flapping its wings in Brazil can, in theory, set in motion a chain of atmospheric events that ultimately leads to a tornado in Texas. This is not a literal statement about insects and storms, but a powerful metaphor for chaos theory, a field of mathematics that explores how tiny, nearly imperceptible changes in initial conditions can spiral into vastly different outcomes. The meteorologist Edward Lorenz stumbled upon this truth in the 1960s while running computer simulations of weather patterns. He found that rounding a number in his data from 6 decimal places to 3, a change so small it seemed insignificant, produced a completely different long-term forecast. His work revealed that many systems in nature, from the flow of water in a river to the complex rhythms of our own heartbeats, are governed by nonlinear equations. These are mathematical relationships where the output is not directly proportional to the input, where a small push can lead to an unexpectedly large result. The beautiful visualization of this idea is the Lorentz attractor, a strange, butterfly-shaped figure that emerges from plotting the solutions to his equations. It shows a system that is entirely deterministic, following strict mathematical rules, yet it never repeats itself and never crosses the same point twice. It is a portrait of chaotic, aperiodic behavior born from perfect order. This understanding has profound applications, helping us grasp why precise weather prediction beyond a week or two remains so challenging and why economic markets can be so volatile. How does chaos contain this hidden order? It reveals that what appears to be random noise is actually the complex output of a deep, underlying mathematical structure. The universe is not merely orderly or chaotic, but exists in a rich space between, where simple rules give rise to an endless tapestry of intricate, unpredictable beauty. Even a perfect vacuum of space is not truly empty. It seethes with a faint quantum energy, a sea of virtual particles flickering in and out of existence. When this quantum foam meets the immense gravity of a black hole, something extraordinary happens. Stephen Hawking realized that at the very edge of a black hole, its event horizon, this quantum activity could allow radiation to slowly leak out. This is Hawking radiation, a process that gives black holes a temperature and implies they are not entirely black. They can, over staggering spans of time, evaporate. This discovery wove together 3 great pillars of physics, general relativity, quantum mechanics, and thermodynamics, into a single, profound tapestry. A black hole, the simplest possible object defined only by its mass, spin, and charge, also possesses entropy. The Bekenstein-Hawking entropy formula describes this, showing that a black hole's entropy is proportional to the area of its event horizon. This is a deeply counterintuitive idea. In our everyday world, entropy is a measure of disorder, and it is related to volume. But for a black hole, the ultimate sink of disorder, the entropy is tied to its surface area. This hints that all the information about what fell into the black hole might not be lost, but could be encoded on its 2-dimensional boundary, a concept that has revolutionized our thinking about space and information. What happens to the information about a star or a book or a person if it crosses the event horizon? According to quantum mechanics, information cannot be destroyed. But if a black hole evaporates and vanishes, where does that information go? This is the black hole information paradox, a puzzle that forces physicists to question the very nature of reality and suggests that our current theories are still incomplete. The mathematics of black hole thermodynamics points toward a deeper, hidden layer of the universe, one where space, time, and information are woven together in a way we are only beginning to comprehend. That faint cosmic static picked up by two radio astronomers in 1965 was no instrument malfunction. It was the oldest light in the universe, a gentle echo of creation itself. This cosmic microwave background radiation is the cooled remnant of the Big Bang's first flash, a snapshot of the cosmos when it was just 380,000 years old. Before that moment, the universe was a searing, opaque plasma of particles and light. As it expanded and cooled, it finally became transparent, releasing that primordial light to travel across space for billions of years. The most astonishing feature of this radiation is its incredible uniformity. No matter which direction you look, the temperature is almost exactly the same, a frigid 2.7 degrees above absolute zero. But nestled within that perfect uniformity are the tiniest of ripples, minuscule variations in temperature, 1 part in 100,000. These fluctuations are not random noise. They are a mathematical treasure map. When scientists plot the size of these temperature variations across the sky, they produce a power spectrum, a specific set of peaks and valleys that reveal the fundamental properties of the cosmos. The precise height and position of the first peak confirms the universe is geometrically flat. The second peak tells us about the proportion of ordinary matter. The third relates to the amount of dark matter. It is as if the early universe left behind a cosmic barcode, and we have learned how to scan it. How could such a faint whisper carry so much information? The answer lies in the physics of sound. In its first few 100,000 years, the universe was a ringing medium, with gravity pulling matter inward and radiation pressure pushing it outward, creating spherical sound waves that traveled through the primordial soup. Those tiny hot and cold spots in the microwave background are the frozen imprints of these acoustic oscillations, the overtones and resonances of the Big Bang itself. Satellites like the Cosmic Background Explorer and the Planck mission have spent years meticulously measuring these patterns, their data providing the most stringent tests for our cosmological models. The mathematical perfection of this power spectrum strongly supports the theory of cosmic inflation, a brief period of unimaginably rapid expansion in the universe's first fraction of a second. Inflation would have stretched quantum fluctuations from the microscopic to the cosmic scale, planting the seeds that, under the steady pull of gravity, would one day grow into all the galaxies, stars, and planets we see today. This ancient light is therefore more than a relic. It is the ultimate cosmic blueprint, a mathematical message from the dawn of time, written in the language of thermodynamics and wave mechanics, waiting billions of years for a conscious mind to finally read it. Einstein's spooky action at a distance is no mere theoretical curiosity. It is a fundamental feature of our reality, where two particles can become so deeply linked that they share a single existence, no matter how far apart they travel. This is quantum entanglement. The mathematics of quantum mechanics predicted this strange bond, describing particles not with definite states, but with probability amplitudes, a cloud of potential outcomes. When two particles become entangled, their probability clouds merge into one mathematical description, a single wave function in an abstract realm called Hilbert space. Observing one particle, say, finding its spin pointing up, instantly resolves the shared wave function, guiding its distant partner into a complementary state, spin down, with no signal passing between them. This is non-locality, a connection that seems to transcend space and time entirely. Alain Aspect's groundbreaking experiments in the 1980s confirmed this breathtaking phenomenon, closing loopholes and showing that the universe truly does allow for these instantaneous correlations. What does this mean for our understanding of reality? It suggests that at its most fundamental level, the universe is not a collection of separate, independent objects. Entanglement paints a picture of a deeply interconnected cosmos, where the properties we observe are not local and predetermined, but are born from a web of relational possibilities. This mathematical framework is now the engine of a technological revolution. Quantum computers use entangled qubits to perform calculations that would take classical computers millennia, exploring many possibilities simultaneously. Quantum cryptography uses the principle that any attempt to observe an entangled message will disturb the delicate link, alerting the users instantly. The universe, it seems, operates on a ledger of probabilities and correlations, written in a mathematical language that goes beyond our everyday experience of space and time. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. This single idea, the heart of Einstein's general theory of relativity, completely rewrote our understanding of gravity. Published in 1915, it proposed that what we feel as gravity is not a mysterious force pulling at a distance, but the natural motion of an object through a universe whose very geometry is shaped by mass and energy. The Sun, for instance, creates a deep impression in the fabric of spacetime. The Earth does not orbit because it is being pulled. It orbits because it is following the straightest possible path, a geodesic, through that curved geometry, like a marble rolling around a funnel. The mathematical language used to describe this curvature is tensor calculus, a complex but beautiful system of equations that captures how every component of space and time interacts. These are Einstein's field equations, which state that the geometry of spacetime is directly related to the energy and momentum within it. One of the theory's first great successes was explaining the subtle wobble in Mercury's orbit, a tiny anomaly that earlier physics could not fully account for. But an even more striking prediction was that this curvature would bend the path of light itself. During the solar eclipse of 1919, Sir Arthur Eddington led an expedition to measure the positions of stars near the Sun's darkened disk. He found their light was deflected by exactly the amount Einstein's equations predicted, confirming that space itself is flexible. This effect, called gravitational lensing, is now a fundamental tool for astronomers, allowing us to use massive galaxy clusters as natural telescopes to see even more distant objects behind them. Another deep consequence is gravitational time dilation. A clock in a stronger gravitational field, like here on Earth's surface, will tick measurably slower than a clock in orbit. This is not a mechanical error. Time itself flows at different rates depending on the geometry of space. This understanding is essential for the global positioning system. The satellites in the GPS network have to account for this relativistic effect, because if they did not, their navigation data would become inaccurate by several miles within a single day. Why does our universe choose to express its most familiar force through such an abstract geometry? General relativity reveals a cosmos where the stage itself is dynamic, where the mathematics of differential geometry is not just a model, but an active description of reality. The equations show us a world that bends, stretches, and breathes with the objects within it, a universe where mathematics literally gives shape to everything. There is a single equation that acts as a cosmic recipe for nearly everything. The standard model Lagrangian is a dense, sprawling mathematical expression that perfectly describes the known fundamental particles and the forces that govern them, with the notable exception of gravity. It is the ultimate culmination of decades of work by brilliant minds like Sheldon Glashow, Steven Weinberg, and Abdus Salam. This one master equation unifies quantum electrodynamics, which governs light and electricity, with the weak nuclear force responsible for radioactive decay and the strong nuclear force that binds atomic nuclei together. It achieves this unification through the elegant language of gauge theories and symmetry groups, mathematical concepts that dictate how particles can interact. The equation itself is a complex tapestry of terms and symbols, each representing a specific particle or a possible interaction. The discovery of the Higgs boson at the Large Hadron Collider was a monumental moment, not because scientists found something entirely unexpected, but because they found the final, crucial piece that this specific mathematical framework had demanded for decades. The top quark, the W and Z bosons, all were first predicted by the mathematics of the Standard Model, long before they were ever observed in a detector. How can one collection of symbols possibly capture the riotous complexity of subatomic reality? It works because the model is built on profound symmetries. The mathematical groups underlying it, with names like SU3 and U1, are like the rules of an intricate dance, specifying which moves or interactions are allowed and which are forbidden. When a muon transforms into an electron and a pair of neutrinos, it is not a random event. It is a direct and predictable outcome written into the Lagrangians' terms. This mathematical object is so powerful that physicists can use it to calculate the outcome of particle collisions with stunning precision. The validation of its predictions by massive machines like the Large Hadron Collider is a testament to the fact that we are not just approximating nature. We are reading from its fundamental blueprint. The Standard Model Lagrangian stands as a pinnacle of human understanding, a profound reminder that the universe's immense complexity can be captured and elegantly contained within the concise, predictive power of mathematics. Our solar system holds a numerical echo from its very formation. In the 1700s, astronomers noticed a curious mathematical pattern in the spacing of the planets. It became known as Bode's law, a simple sequence that starts with 0, then 3, and doubles each time. To get a planet's approximate distance, you just add 4 to each number in the sequence and divide by 10. The results, in astronomical units, line up remarkably well with the orbits of Mercury, Venus, Earth, Mars, and the gap where the asteroid belt resides. When it was first formulated, the pattern pointed directly to an undiscovered world between Mars and Jupiter. Astronomers later found not a single planet, but the countless fragments of the asteroid series, exactly where the sequence predicted something should be. The rule's greatest triumph came with the discovery of Uranus, whose orbit matched the next position in the sequence almost perfectly. This was not a fundamental law of physics like gravity, but it was a compelling clue, a mathematical rhythm written into the architecture of our cosmic neighborhood. The pattern, however, began to unravel with Neptune, whose orbit fell far from where Bode's law predicted, and it completely fails for Pluto. So is this just a numerical coincidence, a cosmic fluke? The ongoing debate touches on a profound question. Could this apparent order be a natural byproduct of how planetary systems form? As a cloud of gas and dust collapses to form a star, the material in the surrounding disk may naturally settle into regions of stability and instability, perhaps governed by gravitational resonances that herd planets into specific orbital lanes. We now see similar spacing in some exoplanetary systems around other stars, suggesting that such patterns might be a common, though not universal, feature of cosmic construction. Bode's law may not be a true law, but its persistent whisper hints at an underlying tendency for matter to arrange itself according to a deep, mathematical grammar. A passing siren's wail shifts from a high pitch to a deep drone, a familiar sound that holds a secret to the cosmos. This is the Doppler effect in action, the same principle that applies to light, allowing us to read the story of the universe's expansion in the color of starlight. When a galaxy moves away from us, the waves of its light are stretched, shifting its color toward the red end of the spectrum. In the 1920s, Edwin Hubble carefully measured this redshift from distant galaxies and made a breathtaking discovery. The farther away a galaxy was, the greater its light was redshifted, meaning it was moving away from us at a faster velocity. This relationship, now known as Hubble's law, is mathematically elegant in its simplicity. The velocity of a galaxy's recession is directly proportional to its distance from us. The equation is a simple proportion, v equals h0 times d, where h0 is the Hubble constant. This single, clean mathematical relationship revealed a universe that is not static, but dynamically and uniformly expanding in all directions. How can one equation change our entire cosmic perspective? It provided the first compelling evidence for the Big Bang theory, the idea that our universe began in an immensely hot, dense state and has been stretching outwards ever since. The redshift of a galaxy is more than just a speedometer. It is a window into the past. By measuring how much the light has stretched, astronomers can calculate not only how fast the galaxy is receding, but also how long that light has been traveling to reach us, looking back billions of years into cosmic history. This mathematical tool allows us to trace the expansion backwards to the very beginning, to map the large-scale structure of the cosmos, and to even discover the mysterious dark energy that now seems to be accelerating this grand unfolding. That simple change in a siren's pitch, translated to the domain of light, gives us a direct line to the universe's greatest story, written in the universal language of proportion and shift. Every complex wave, from a symphony to a star's shimmer, can be understood as a sum of pure, simple tones. This is the profound insight of Fourier analysis, a mathematical lens that reveals the hidden harmonies within any signal. In the early 1800s, Joseph Fourier developed a powerful method to break down intricate functions into a series of basic sine and cosine waves, each with its own frequency and amplitude. This technique, the Fourier transform, is like a master chef tasting a complex stew and identifying every single ingredient that went into the pot. It allows us to take any messy, complicated waveform and see the precise recipe of simple frequencies that build it. Why is this so transformative? Because it translates a signal from the domain of time or space into the domain of frequency, unveiling patterns that were completely invisible before. An astronomer points a telescope at a distant star. The light it collects is a tangled mix of countless wavelengths. By applying a Fourier transform to this incoming light, the scientist can separate it into its constituent colors, creating a spectrum. Dark lines in that spectrum correspond to specific elements in the star's outer atmosphere, each element absorbing a unique set of frequencies. This is how we know the Sun is made mostly of hydrogen and helium. We are quite literally doing cosmic chemistry from 93 million miles away, all by listening to the mathematical music of the light. The same principle cleans up our digital lives. That grainy photograph from a security camera can be sharpened because the image is treated as a two-dimensional signal. The transform separates the clear, important features from the random visual noise, allowing software to reduce the noise and enhance the true picture. Your digital music files use a related method to compress audio, removing frequencies the human ear is unlikely to hear, all to save space without sacrificing quality. This mathematics is the silent engine of our connected world, essential for Wi-Fi, mobile phones, and medical imaging. An MRI machine does not take a literal picture of your body. It measures magnetic signals and then uses a Fourier transform to reconstruct those signals into the incredibly detailed cross-sectional images doctors rely on. From the secret composition of a star to the inner workings of the human brain, Fourier analysis demonstrates that complexity is often just simplicity woven together in intricate ways. It proves that beneath the surface chaos of our world, a fundamental harmonic order is waiting to be heard. Hidden within the laws of physics is a principle of profound elegance, a link between the beautiful and the unchanging. The deep connection between symmetries in nature and conserved quantities was formalized by the mathematician Emmy Noether in 1918. Her revolutionary theorem states that for every continuous symmetry in a physical system, there is a corresponding quantity that is conserved. This idea uses the powerful framework of Lagrangian mechanics, which describes how systems evolve along paths of least action. Consider the simple fact that the laws of physics are the same today as they were yesterday. This time translation symmetry, the idea that an experiment will yield the same result regardless of when you perform it, directly implies the conservation of energy. The total energy in a closed system can neither be created nor destroyed, it can only change form. This is not a separate rule, but a direct mathematical consequence of the universe's temporal symmetry. Similarly, the rotational symmetry of space, the fact that the outcome of an experiment does not depend on which direction you face your laboratory, leads directly to the conservation of angular momentum. A spinning ice skater pulls her arms in and spins faster not because of a new force, but because her angular momentum, a product of her mass, speed, and distribution, must remain constant. How does Noether's theorem bridge the abstract world of mathematics with the tangible reality of physics? It reveals that the most fundamental laws we observe, the conservation of energy, momentum, and charge, are not arbitrary decrees. They are rooted in the geometric invariance of the universe itself, in the hidden symmetries of the cosmic stage upon which all events play out. This single mathematical insight unifies concepts across every field of physics, from the predictable arc of a cannonball in classical mechanics to the intricate dance of particles in quantum field theory. It shows us that the enduring constants of our reality are the direct expression of an invisible, perfect order. A single, simple equation gives birth to an infinite cosmos of unparalleled intricacy. The Mandelbrot set emerges from the humble rule z equals z squared plus c, where z begins at 0 and c is any point on the complex plane. You feed the output back into the equation again and again, watching to see if the value remains bounded or if it grows without limit. The result of this iterative process is not a bland graph, but a boundary of infinite depth and complexity. Zoom into its jagged edge, and you will find an endless procession of miniature Mandelbrot sets, each one surrounded by its own swirling tendrils and seahorse spirals. This is the ultimate expression of self-similarity, a fractal where the whole is mirrored perfectly in its tiniest parts. Benoit Mandelbrot's great insight was to harness computing power to visualize this mathematical object, revealing a hidden world of stunning beauty that pen and paper alone could never uncover. The set has since become a cultural icon, its psychedelic, organic forms inspiring digital artists and offering mathematicians a deep well of unanswered questions. Why does such a basic rule generate a structure of such boundless richness? The answer lies in the sensitive dependence of the equation on its initial input. A minuscule shift in the value of c, a change smaller than the size of an atom on your screen, can shift the calculation from a stable, bounded orbit into a wild, runaway escape. This is the heart of complex dynamics, a field where simple, deterministic rules produce wildly unpredictable and evolving outcomes. The Mandelbrot set is the map of this behavior, with its dark interior representing stability and its spectacularly colored exterior painting a picture of how quickly values diverge. It is a perfect visual metaphor for chaos theory itself, demonstrating how a universe of infinite variation can be encoded within a seed of perfect simplicity. This is not just an abstract wonder. The same mathematical principles that generate the Mandelbrot set are used to create realistic landscapes in films and video games, simulating the rough, fractal texture of mountains and clouds. It stands as a profound reminder that the universe may not favor simplicity or complexity, but rather the elegant, iterative processes that effortlessly transform one into the other. Even the vacuum of space is not a featureless void. It hums with an unseen field, a cosmic molasses that gives substance to the universe itself. This is the Higgs field, and its interaction with particles is what we experience as mass. The mathematical concept, known as the Higgs mechanism, was proposed in the 1960s by Peter Higgs and several other theorists. Their work showed how a field could permeate all of reality, and how its structure could break a fundamental symmetry in nature. This process, called spontaneous symmetry breaking, is key to understanding why our universe has the properties it does. Imagine a ball balanced perfectly on the peak of a steep hill. This state is symmetrical, but it is also unstable. The slightest nudge will send the ball rolling down into the valley below, settling into one specific, stable point. The symmetry of the hilltop is broken, but a new, stable reality emerges. The Higgs field exists in such a broken symmetry state everywhere. As fundamental particles move through this field, they interact with it. Some particles, like photons, simply do not interact at all. They slip through the cosmic molasses without any resistance, and thus they have no mass and travel at the speed of light. Other particles, like electrons and quarks, do interact. They experience a kind of drag, a resistance to their acceleration. This resistance is what we define as inertial mass. The mathematics describing this uses potentials and gauge symmetries, showing how an empty vacuum can possess a rich, hidden structure that defines the very nature of matter. The discovery of the Higgs boson in 2012 at the Large Hadron Collider at CERN was a monumental event. This particle is not the field itself, but a crucial excitation of it, a ripple in the cosmic molasses that confirmed the field's existence. Its detection validated a decades-old prediction, proving that the mass of the objects around us, and even within us, is not an innate property. It is a gift from an invisible cosmic field, an emergent property arising from an underlying mathematical order. How does nothingness give rise to something? The Higgs mechanism reveals that what we perceive as empty space is a stage with a hidden architecture, and that the most fundamental property of matter, its mass, is written in the language of quantum field theory. A single mathematical expression dares to quantify our cosmic loneliness. The Drake equation, conceived by astronomer Frank Drake in 1961, is not a tool for finding aliens, but a framework for thinking about the possibility of intelligent life in our galaxy. It is a chain of probabilities, a series of terms that are multiplied together. The equation begins with the rate of star formation, a number we can estimate with some confidence. Then it introduces a cascade of uncertainties. What fraction of those stars have planets? How many of those planets are habitable, orbiting in the just right Goldilocks zone where liquid water could exist? On how many of those suitable worlds does life actually arise? And then the great leap, How often does that life evolve to become intelligent and technologically communicative? The final factor is the most haunting, the length of time such a civilization might last, broadcasting its existence into the void. When you multiply all these factors together, the result is n, the estimated number of civilizations in the Milky Way with whom we might potentially communicate. The numbers you plug in can lead to wildly different conclusions, from a galaxy teeming with voices to a profound and empty silence. This is the heart of the Fermi paradox, the jarring contradiction between the high probability of extraterrestrial life and the utter lack of any evidence for it. So where is everybody? The Drake equation does not answer that question, but it gives us a structured way to explore it. It forces us to confront the gaps in our knowledge, transforming a philosophical wonder into a scientific research program. It guides our search for exoplanets and our analysis of atmospheric biosignatures. It connects astronomy directly to biology and even sociology, asking profound questions about the longevity of technological species. Could it be that the final term, the lifetime of a communicating civilization, is tragically small for most? The equation uses the language of probability not to give us a final number, but to map the boundaries of our ignorance. It is mathematics employed as a tool for humility and wonder, a constant reminder that the universe has written its most profound secrets in a code we are only beginning to decipher. That elegant wave function is the beating heart of the quantum world, a mathematical guide that holds all the possibilities for a particle's location and state. This probability cloud is governed by a single, powerful equation, formulated by Erwin Schrödinger in 1926. His equation is a master key to the subatomic realm, using the language of partial differentials to model how quantum systems evolve. It does not tell you where an electron is at any given moment. Instead, it describes a wave of probability, a map of potential outcomes. The equation is beautifully deterministic for this wave function itself, meaning that if you know its state at one moment, you can calculate precisely how it will ripple and change into the future. Yet when we make a measurement, that single, certain wave function resolves into a single, definite result, a process governed by pure chance. This is the central quantum mystery, the strange transition from a world of many possibilities to the one reality we actually observe. How can a perfectly predictable equation yield such unpredictable outcomes? The answer lies in the difference between the wave function's evolution and the act of observation. The Schrödinger equation is the reason chemistry exists. It predicts the specific quantized energy levels that electrons can occupy around an atomic nucleus. These are not arbitrary orbits but stable, wave-like patterns, the mathematical solutions to Schrödinger's equation for the hydrogen atom. The shapes of these orbitals, the s orbitals like a sphere and the p orbitals like dumbbells, are not just convenient drawings. They are direct visualizations of the wave function itself, showing the regions in space where an electron is most likely to be found. This mathematical insight explains the very structure of the periodic table and the nature of chemical bonds. When two atoms share electrons to form a molecule, their individual wave functions merge and overlap, creating a new, combined probability distribution that binds them together. The stability of every molecule in your body, the very possibility of life, is a direct consequence of this single, elegant equation. It provides a mathematical window into a reality where objects exist as distributions of probability, where the act of looking invites the universe to make a choice, and where the solid world we experience is built upon a foundation of beautiful, shimmering uncertainty. Our universe underwent a growth spurt of unimaginable speed in its very first moments. A fraction of a second after its birth, space itself expanded exponentially, inflating from a subatomic speck to a vast cosmic volume faster than light could cross it. This is the theory of cosmic inflation, a concept proposed by physicist Alan Guth to solve profound puzzles about our cosmos. One of these is the horizon problem. When we look at the cosmic microwave background, the oldest light in the universe, we see it has the same temperature in all directions. But according to the standard Big Bang model, these distant regions of the sky were never in contact with each other. They were beyond each other's cosmic horizons, with no time for heat to flow between them and even things out. How could they be so perfectly uniform? Inflation provides the answer. It suggests that all these regions were indeed in close contact before the inflationary epoch began. A tiny, uniform patch of the primordial universe was then stretched to become the entire observable cosmos we see today, preserving that initial uniformity across an immense scale. The mathematics behind this is drawn from field theory. Physicists describe inflation using a scalar field, often called the inflaton field, which permeated the early universe. This field possessed a peculiar form of potential energy that acted like a kind of repulsive gravity, causing space to stretch at an accelerating rate. The equations show that this expansion was driven by the field's vacuum energy, a state of negative pressure that pushed the fabric of spacetime apart. This process did not last forever, as the inflaton field eventually rolled down its potential energy hill. That tremendous energy had to go somewhere. It decayed, reheating the universe and filling it with the hot plasma of particles and radiation that would become the stuff of stars and galaxies. Why is this theory so compelling? Because its mathematical predictions match our observations with stunning accuracy. Inflation naturally produces a universe that is geometrically flat, which aligns perfectly with the data from the cosmic microwave background. More importantly, it provides the origin story for all cosmic structure. The inflaton field was not perfectly uniform. It was subject to tiny quantum fluctuations, random jitters on the smallest possible scales. Inflation stretched these microscopic ripples to cosmic proportions, imprinting them as faint density variations in the early universe. These tiny seeds, this primordial roughness, are the very things that gravity would later amplify into the great cosmic web of galaxies and voids we observe today. The theory of cosmic inflation elegantly connects the quantum world to the cosmic stage, showing how the smallest fluctuations in a mathematical field could ultimately dictate the large-scale architecture of everything we see. The spots on a leopard and the stripes of a zebra are not painted on by chance. They are the visible signature of a hidden mathematical process, a phenomenon first explained by Alan Turing in 1952. His groundbreaking work revealed that patterns throughout nature can emerge spontaneously from a simple system of interacting chemicals. He called this a reaction diffusion system. Imagine two invisible substances, an activator and an inhibitor, spreading through a developing embryo or a field of vegetation. The activator promotes its own production and creates a feature like a dark spot. The inhibitor, which moves more quickly, works to suppress the activator, preventing spots from forming too close together. This push and pull, guided by a set of differential equations, creates a stable, repeating pattern out of initial uniformity. It is a mathematical recipe for biological order. This process explains the regular spacing of a cactus's spines, the intricate walls on a seashell, and the stunning array of coat patterns across the animal kingdom. How can such a simple mathematical model account for so much of life's beautiful diversity? Turing patterns reveal that the blueprint for form itself is written in the language of instability and diffusion. An embryo does not contain a microscopic map of the stripes it will grow. Instead, it carries out a simple chemical program, and the pattern emerges as a natural consequence of the mathematics. This bridges a profound gap, showing that the logic of biology is deeply intertwined with the principles of mathematics. The same equations that describe the spread of a chemical can also model the distribution of vegetation across a savanna, where plants act as activators for their own growth and inhibitors for their neighbors, creating clusters and arrangements in the landscape. Turing's work suggests that the universe has a preferred toolkit for creating order, and that one of its most powerful tools is a system where simple components, following simple rules, can self-organize into breathtaking complexity. The diversity of life in all its forms may be the ultimate expression of a hidden, spontaneous mathematics. The night sky has always been a canvas for numbers. Long before telescopes, ancient Babylonian priests tracked the wandering planets, recording their positions on clay tablets with astonishing numerical precision. They were not merely stargazers, they were the first cosmic accountants, using early geometry to predict lunar eclipses and the rhythms of the seasons. This human urge to find pattern in the celestial dance was then refined by the Greeks, who insisted the universe itself was built from geometry. Plato declared the heavens must move in perfect circles, for the circle was the most divine and rational shape. To make this beautiful idea fit the awkward, looping paths of the planets, Claudius Ptolemy constructed an elaborate mathematical model of crystal spheres and epicycles, smaller circles riding on larger circles. It was complex, but it worked, offering a predictive, mathematical description of the sky that held for over 1,000 years. Then came a quiet revolution. Nicolaus Copernicus, a Polish cleric, dared to place the sun at the center, not for poetic reasons, but because it created a simpler, more elegant mathematical system. His heliocentric model did not immediately improve predictions, but it revealed a more harmonious underlying order, a symphony where the planets moved in unified, sun-centered circles. What drove these pioneers across the centuries? It was a conviction that the cosmos was not a chaotic realm of gods and monsters, but a rational construction, a clockwork of divine logic whose language was mathematics. This quest culminated with Isaac Newton, who saw the apple fall and the moon orbit not as separate events, but as one phenomenon. He invented an entirely new form of mathematics, calculus, to describe it. His law of universal gravitation was a single, breathtaking equation that could predict the motion of a thrown rock here on Earth and the elliptical path of Mars around the Sun. In one stroke, he unified the heavens and the earth, proving they obeyed the same mathematical rules. This historical journey reveals a profound truth. Our understanding of the cosmos has never been a simple collection of facts. It is a story written in the evolving language of mathematics, a continuous human effort to read the hidden code of reality itself. This hidden mathematical order is the silent music of the cosmos, a composition written in the language of numbers that we have only just begun to understand. Our journey through these 25 phenomena reveals a universe that is not merely described by mathematics, but one that is fundamentally mathematical in its very essence. From the spiral of a galaxy to the quantum dance of a particle, these are not separate mysteries. They are different verses of the same universal poem, a poem written in a code of incredible elegance and power. This code is not something we invented and then imposed upon the world. We discovered it. We are learning to read a language that was already there, waiting in the petals of a flower and the depths of a black hole. This realization invites a profound sense of awe, a feeling that our search for knowledge is a participation in something far grander than ourselves. Each pattern we uncover, from the golden ratio to the standard model, is a clue in the greatest detective story of all, the story of reality itself. And the most beautiful part of this story is that it has no final chapter. Every answer we find peels back a layer to reveal new and deeper questions, an endless invitation to explore, to wonder, and to appreciate the breathtaking elegance of existence. The cosmic detective work continues, and the next discovery is waiting for you. What piece of this mathematical universe resonates most deeply with you? Share your thoughts and let us keep exploring the wonders that connect us all.